Okay, so what I am planning to do in the next few lectures is to study the case of complex tori. Okay, so let me recall what a complex torus is. So if you remember, we choose two complex numbers omega 1, omega 2, which are non-zero. Okay, and so we fix this and assume that their ratio is not a real number. Okay, which means they are linearly independent over R. Okay, and then we look at the subgroup of Mobius transformations which correspond to translations integer translations by integer multiples of omega 1 and omega 2. Okay, so you look at z going to n times so z going to z plus n times omega 1 plus m times omega 2. You look at all these translations by integer multiples of omega 1 and omega 2. Okay, integer linear combinations of omega 1 and omega 2 where n and m are integers. Okay, and this is of course these are Mobius transformations, and you see being translations the only fixed point that they have is the point at infinity. Okay, so these form a subgroup of the holomorphic automorphisms of the complex plane. Okay, so the point at infinity is mapped to the point at infinity, the rest of it is going to be the complex plane. So the complex plane is any finite complex number is mapped to a finite complex number. Okay, so you see this group this subgroup of course is abelian. Okay, and it can be identified with z dot translation by omega 1. So in fact I can write it like this, cross z dot translation by omega 2, right, which is eventually which is actually isomorphic to z cross z, right. And what you do is you take the complex plane, all right, and then you go modulo this subgroup. Okay, so you go C modulo the subgroup z translation by omega 1 cross z dot translation by omega 2, and this gives you a complex structure, a Riemann surface structure on the torus. Okay, which we call as let me put T sub omega 1 comma omega 2. Okay, so this is a Riemann surface structure on this, which is topologically a torus, a real torus. Okay, and this map is a covering map. This is a universal covering because C is simply connected, all right, and this covering map, if I call it as P omega 1 sub P sub omega 1 comma omega 2, then this is a universal covering. This is a universal covering, and because of this the fundamental group of this is identified with the deck transformation group of this cover, and the deck transformation group is precisely this. Okay, so by one, so if I choose for example point, let's say 0, okay, and suppose the point 0 goes to a point x here, okay, then I have the identification fundamental group of this torus T sub omega 1 comma omega 2 based at x is identified with the deck transformation group of this covering, which is P sub omega 1 comma omega 2, and this deck transformation group is precisely this this group of translations, Z dot translation by omega 1 cross Z dot translations by omega 2, which is exactly the same thing. Okay, so in fact I shouldn't even write isomorphic to, in fact it's actually equal to. Okay, and of course this is the deck transformation group, which is sitting inside the group of automorphic the holomorphic automorphisms of the universal covering space, which you know is P delta 2C. If you write it out as matrices, these are all elements of PSL 2C with which are of upper triangular form, alright. Fine. So the question is we want to look at so we want to look at various possible Riemann surfaces that you can get in this way, which to begin with you would get by varying omega 1 and omega 2, alright. So the question is what is the set of all tori, complex tori omega 1 comma omega 2, where omega 1 comma omega 2 are complex numbers non-zero and with non-real ratio omega 1 by omega 2 not a real number. So this is a set of all possible complex tori, alright, and then you want to go modulo holomorphic isomorphism. Okay, so that means I am looking at holomorphic isomorphism classes of complex tori, okay, and I want to know how many of them are there. Namely, I want to know what is the set, alright. Now well, of course the answer to this question is the following theorem, which I had stated earlier. So let me recall this. Okay, the set of holomorphic holomorphic isomorphism classes of complex tori can be naturally identified with the set U mod PSL to Z, which is the set of orbits of PSL to Z in U, in the upper half plane U. Okay, this is a set of all Z in C such that imaginary part of Z is greater than 0. Okay, so that set is naturally identifiable with U mod PSL to C, and when you have a set modulo group, what one means is of course the orbits of the group on that set, for the group action on that set. Okay, so I want to tell you one thing, namely recall that the holomorphic automorphisms of U are elements of PSL to R. Okay, and PSL to Z is a subgroup of PSL to R, and therefore PSL to Z also acts on U. Okay, if a group acts on a set, then a subgroup also acts on the set, and you can also talk about orbits for that subgroup. Okay, and that's exactly what we are doing here, and the fact is that if you take the orbits, this set is exactly the set of complex tori up to holomorphic isomorphism. Okay, so this is the first statement. Then there is more. The more interesting statement is that this set U mod PSL to Z acquires naturally the structure of a Riemann surface okay, and that Riemann surface happens to be isomorphic, that is holomorphically isomorphic to the complex plane, okay. Further, U mod PSL2Z acquires naturally the structure of a Riemann surface holomorphically isomorphic to the complex plane, okay. So the upshot of the theorem is that this set is actually a Riemann surface, and what is that Riemann surface? It is just the complex plane. So so it is amazing that this set has a Riemann surface structure, and that the Riemann surface is the complex plane, okay. So this is what I would like to prove, set out to prove in the next few lectures, okay. So there are two tasks that we will have to do. The first thing is how to identify this set with the set of orbits of PSL2Z on U, that is one step. The next step is to explain how U mod PSL2Z becomes a Riemann surface, okay, and how that Riemann surface is biholomorphic, that is holomorphically isomorphic with the complex plane, okay. So this is what we are going to do. So so I will begin with trying to show that this set is bijective with U mod PSL2Z, okay. So the first thing I want to state is that just for the sake of novelty, note that set of complex tori modulo holomorphic isomorphism is also the same as, well, these are all going to be, notice, let us recall a theorem. If X is a Riemann surface with fundamental group isomorphic to Z cross Z, okay, then X has to be a complex torus, okay. So that is a theorem that we have proved. So I can just write this also as a set of well I should not write set of and also put a bracket, but let me not be too pedantic about this. So let me just say, I hope it is all right. So let me rub this off, okay. So here I can also write as Riemann surfaces X with pi1 of X comma some base point does not matter, isomorphic to Z cross Z, okay, modulo holomorphic isomorphism, okay. One can also state it like this: you are looking at all those Riemann surfaces with fundamental group isomorphic to Z cross Z, and you are studying them up to holomorphic isomorphism, okay. Yeah, so in this sense what you are doing is, well, you are looking at various possible Riemann surface structures that you can put on a real torus, okay. The underlying structure is a topological real torus, and then you are looking at various Riemann surface structures that you can put on this and trying to look at how many non-isomorphic structures you get, okay. So there is an underlying structure which is the structure of the real torus, alright, and there is a superimposed structure which is that of a Riemann surface, okay, and the question is how many extra structures can you give for the same underlying structure. So this is exactly what is called a moduli problem, okay, in its simplest form. You have a fixed structure on an object and then you know that you can put an extra structure on it. The question is how many extra structures, non-isomorphic extra structures that you can put on that, okay, and if you look at the set of all those structures, does it have a geometry, okay, that is the question of moduli, okay. and we get a beautiful theorem in the case of complex tori. So this is the first case where you get a beautiful theorem on moduli. Okay, so this note was just for fun. Okay, now well, now I am going to make a small the first thing is where did the upper half plane come into the picture? Okay, so you can ask this question, where does the upper half plane come into the picture? It comes because of the following thing, because you can, given any torus like that, you can normalize it. Okay, so here is a lemma. Okay, the lemma is T, you take this torus T omega 1 comma omega 2. Okay, this is biholomorphic, that is holomorphically isomorphic to the torus omega 1 by omega 2 comma 1. Okay, okay, so which means I literally have these two complex numbers, I divide throughout by omega 2, so the second one becomes 1, the first one becomes omega 1 by omega 2. Okay, and in the same vein, so is also biholomorphic to, well, the torus T of well, omega 2 by omega 1 comma 1. Okay, of course I could have divided by omega 1, right. So now what I want to tell you is that so I want to tell you what this lemma means with respect to u. You see, omega 1 by omega 2 is not real, it is a non-real ratio, so it is a complex number, it has an imaginary part, and then if you take the imaginary part, then either omega 1 by omega 2 or omega 2 by omega 1 has an imaginary part which is positive. Okay, and then you choose the one that has imaginary part positive and call that as tau. Okay, and then that tau is an element of u. Okay, so what I am trying to say is that choose tau to be well, omega 1 by omega 2 or omega 2 by omega 1, so that the imaginary part of tau is positive. Okay, you can do that. I mean, one of them has to have, if one of them has imaginary part negative, then the other one will have imaginary part positive. Okay, so what is going to happen is you choose the one that has imaginary part positive. Okay, then you have tau in the upper half plane. Okay, and T omega 1 comma omega 2 is biholomorphic to maybe there isn't enough space here, let me write it the next board. Okay, then tau belongs to u, and the torus T omega 1 omega 2 is biholomorphic to, well, T tau comma 1. Okay, so the moral of the story is that instead of looking at all possible tori like this, it is enough to normalize these two complex numbers in such a way that one of them is an element of the upper half plane and the other one is 1. Okay, so what this lemma says is that it is enough to look at T tau comma 1 with tau in u, that is all right, with tau in u, so real part of tau is greater than 1. So what is the upshot? So let me write that down. Hence set of T omega 1 comma omega 2, well, omega 1 comma omega 2 in non-zero complex numbers, omega 1 by omega 2 are not real, is exactly the same as the set of T tau comma 1 where tau is in u. okay. So so it's enough to look at only complex tori of this form up to isomorphism, okay. So in fact maybe I should not just simply write like this, I should write mod isomorphism. So mod isomorphism is equal to this mod isomorphism, okay. In fact I should write mod isomorphism, not exactly set theoretically, okay. So instead of looking at isomorphism classes here, I can as well look at isomorphism classes here, okay. Now what is the proof for this lemma? The proof of this lemma, so that's where U comes into the picture, okay. That's where U comes into the picture. So in fact what's happening is that you have so let me write that down. So you have actually a map. So we get a map from U to the set of all Riemann surfaces, the set of all complex tori mod isomorphism. Namely, you just send tau to the isomorphism class of T tau comma 1, okay. So you have a map like this, and now you know what it is that we are trying to prove. We are just trying to prove that this map factors to the quotient U mod PSL2Z, which is the orbits of PSL2Z in U, and that and when it factors, it gives rise to a bijective map with this. That will tell you that the set of isomorphism classes of complex tori is naturally identifiable with the orbits of PSL2Z on the upper half plane, okay. So let's give the proof of the lemma. This is pretty easy to prove. So what we have is so let me write out the universal coverings for these two. So I have C to, I have this projection omega 1 comma omega 2, then here I have the torus, complex torus defined by omega 1 and omega 2, okay. And I have on the other hand C to there is this projection tau comma 1, and I have the complex torus tau tau comma 1, okay, where tau is where let me take tau to be omega 1 by omega 2 if you want, okay. Of course I could have also equally taken tau equal to omega 2 by omega 1, right. Now what you do is define this map B of Z is Z by omega 2, okay. Look at this map B of Z is equal to Z by omega 2. Now that map I can divide by omega 2 because omega 2 is not 0, and then it is going to take the complex plane onto the complex plane, alright. It is a Mobius transformation, and it has so it's a holomorphic automorphism of C. It's a holomorphic automorphism of C, okay. And let's see what it does. See, notice that this is just C mod an equivalence relation, which is the equivalence relation is, so there is an equivalence relation, let me put it equivalence sub omega 1 comma omega 2, and what is this equivalence sub omega 1 comma omega 2 is, you see Z1 is equivalent under this relation to Z2 if and only if, okay, Z1 is Z2 plus an integer linear combination of omega 1 and omega 2, let me say n1 omega 1 plus n2 omega 2, okay. And this is exactly the equivalence, okay. I mean, this is another way of saying that you are going modulo translations by integer multiples of omega 1 and omega 2, alright. And you have a similar statement here. This is the complex plane modulo the equivalence relation given by tau comma 1, alright, and this, well the definition is similar to this, okay. And now what I want you to understand is that what does B do to a point like this. If you remember, these were points of these were the points of a grid of parallelograms, okay, and we were actually going modulo that grid, okay. And see what B does to a point like this. B takes n1 omega 1 plus n2 omega 2 to, well, B is supposed to be division by omega 2, so what I am going to get, I'll get n1 tau plus n2, okay, I'll get n1 tau plus n2, but n1 tau plus n2 is a point of this grid, okay. The grid here is a grid which is given by tau and 1, okay. You form a parallelogram with edges 1 and tau, okay, and then you repeat this parallelogram, you get a grid of parallelograms, and the endpoints of the grids, the vertices of the grid, are precisely these elements of this form, okay. So what B does is it takes this grid to that grid, okay, and because of this because of the fact that these are just because of the fact that these are equivalence relations going modulo those grids, you are going to get a map like this. I'm going to get a beta, okay. I'm going to get a beta such that this diagram commutes, right. So this implies that at least set theoretically, okay, I'm going to get a map a beta, okay, get map beta from this torus to this torus, okay. Now the point I want to make is that of course this map is a bijective map because I have B inverse. B is after all an isomorphism. B inverse will be multiplication by omega 2, alright. So B inverse will also map a point like this to a point like this, okay, that will also take the grid here to the grid here. So B inverse is going to induce an inverse for beta, okay. So beta is actually a bijective map, okay, so which is bijective with inverse gotten from B inverse in exactly the way we got beta from B, okay. So I get a bijective map, okay. Now I want to say that this bijective map is actually biholomorphic map, okay. So why is it biholomorphic? It's biholomorphic for the following reason, okay. So let me break this diagram down into two commutative diagrams, okay. So this is B followed by p tau 1, okay. This is holomorphic and this is holomorphic. Mind you, the holomorphic structure on this was inherited from the holomorphic structure above, and once you fix this holomorphic structure, this covering projection becomes a holomorphic map. It's a covering in the holomorphic sense, okay. Therefore this is holomorphic, this is holomorphic, therefore this is holomorphic, okay. And this map is a covering map, so it's locally invertible, it's locally biholomorphic, therefore this is this followed by this locally, okay. But then again this is also a composition of holomorphic maps, and therefore this is holomorphic, okay. So the moral of the story is that the map beta is holomorphic, so it's an injective holomorphic map, so it's a biholomorphic map, okay. So beta is a biholomorphic map, and this literally tells you that this torus and this torus are holomorphically isomorphic, okay. So it's a very simple lemma, alright, fine. So the advantage, as I told you, of this lemma is that it's enough to look at only tori which are given by points on the upper half plane, right, fine. Now let me go ahead and try to say that we get an identification of these the isomorphism classes of these set of isomorphism classes of these tori with U mod PSL2C, okay. So well So suppose so let me start the argument like this because I think it will be very ideal for the exposition. Yes, correct. So suppose the isomorphism class of T tau 1 comma 1 is equal to the isomorphism class of T tau 2 comma 1, where tau 1 and tau 2 are the half plane. Okay, suppose they are isomorphic. So this means that the torus defined by tau 1 is isomorphic, holomorphically isomorphic to torus defined by tau 2. Okay, now again let's draw the covering maps. So I have C, so I have this is P1 and this is T tau 1 comma 1. Okay, then I have again C, this is P2 and I will have T tau 2 comma 1. Okay, and since it's given that these two are holomorphically isomorphic, let me choose an isomorphism. Okay, let me call it something, let's say F. So I am given a holomorphic isomorphism F between these two tori. Okay, and what I am going to do is, using this and covering space theory, I am going to cook up an element of PSL to Z that moves tau 1 to tau 2. That is what I am going to do. Okay, so yeah, so how am I going to do this? So you see, because of this map, so let's look at this whole diagram. All right, the first thing is, as we have done in the case of as we have done earlier, see, if I take this composition, okay, this is a holomorphic isomorphism, this is a covering, therefore this continues to be a covering. Okay, so this is just P1 followed by F, that is what this is, and this is also a covering. All right, and by the universal lifting properties of coverings, this lifts to a map here. Okay, so for that I will have to do some work. Let me choose 0 here. Okay, and let's assume that 0 goes to, let's say, a point x1 here. Okay, and let me assume that f of x1 f takes x1 to x2. Okay, and let me fix a point, let me call this as well, I don't even need to put 0, maybe I put z1, let me call this as z2, fix a point z2 which goes to x2. Okay, so P1 takes z1 to x1, P2 takes z2 to x2, f takes x1 to x2. All right, and I can lift this f circle P1 to a map f circle P1 tilde. Okay, which I would like to call as let me call this as B. Okay, such that this diagram commutes. All right, and well, this map B is going to be holomorphic isomorphism, because I can construct an inverse. I can construct an inverse simply by taking F inverse. Okay, just as I got B from F, I will get B inverse by looking at F inverse, because F is an isomorphism. All right, so B is an element of it's a holomorphic automorphism of C, so it's an element of P delta to C. All right, so B can be identified with you can give it a matrix representative in PSL to C, namely A, B, 0, D. Okay, and it's in PSL, so AD is 1, so D is 1 by A. Okay, so B will look like so this will just look like A, B, 0, 1 by A, right, and of course, so this means that B is the Mobius transformation B of Z is equal to A Z plus B by 0 Z plus D. Okay, which is how all automorphisms of holomorphic automorphisms of C look like, right. Now one needs to look at what's happening to the deck transformation group because of this, okay. So this is a map, this is a whole diagram of spaces, okay. You know that forming the fundamental group is functorial, so I am going to get a corresponding diagram for the fundamental groups. So let me write that down. So what I am going to get is I will have here the fundamental group, first fundamental group of this torus based at x1, that is going to be identified with the deck transformation group of this covering, which is deck of P1, okay, and this F is going to give me an isomorphism F lower star, okay, which is, you know, take a loop at x1, you can produce a loop at x2, okay, which is just well, you just take the image of this loop there, right, and do this for homotopy classes, right. So this F lower star is what you get naturally because the formation of the fundamental group is functorial, right, and here what I will get here is the fundamental group of this other torus T tau 2 comma 1 based at x2, right, and that is well identified with the deck transformation group of P2, alright, and you also have one more, there is also a map like this. So this is also a covering. Because of this covering I will get an identification of this, the fundamental group of this, namely this, with the deck transformation group of this cover, okay, but then this followed by this is this. So what it will actually tell me is that this is the same as the deck transformation group of F circle P1, okay, these will be one and the same, okay. This is for example I proved this explicitly in the previous lecture, okay, and so this is another identification. This identification comes because of this covering, alright, and because this diagram commutes, this diagram also commutes, and that is the reason why these two are the same, okay. And what about this map? So this map is just you know, conjugation, right, namely if you give me a deck transformation here, how do I get a deck transformation there? What I do is I go like this, apply the deck transformation and then come back, okay. Going like this is applying B inverse, then applying the deck transformation here and then applying B, okay. So it is just a map that sends A to B, A, B inverse, this is just conjugation by B, and this is an isomorphism, okay, because this map is an isomorphism, this is a holomorphic isomorphism, okay. So well the upshot of all this is the following. I have B dot deck P1 B inverse is equal to deck P2, namely the deck transformation group of P1 and P2 are they conjugates in the group of holomorphic automorphisms of C, okay. So I get this. Now let us go and look at what the generators of these deck transformation groups were chosen as, and we will get a little bit more, we can extract a little bit more of information, okay. So well, so we have, see, deck P1, the deck transformation group of P1 has generators z going to z plus 1, z going to z plus tau 1, okay. These are the generators of deck transformation group. After all, the deck transformation group is precisely the subgroup of holomorphic automorphisms that you have to go mod to get this torus, and the subgroup of holomorphic automorphisms here are translations by integer multiples of tau 1 and 1, okay. So you get this, okay, and similarly deck P2 has generators z going to z plus 1, z going to z plus tau 2. Notice that these two are they are isomorphic to the corresponding fundamental groups, and the fundamental groups are just z cross z, okay. Therefore there are two generators, okay. Now you see, so if you look at this, what this will tell you is that if I take z going to z plus 1, then it is a conjugate of an element here, okay, and similarly z going to z plus tau 2 is a conjugate by b of an element here, okay. So so let me write down what I have worked out. So you can write z going to z plus 1 is equal to b z going to z plus alpha tau 1 plus beta dot b inverse, and z going to z plus tau 2 is b dot conjugation by b of z going to z plus gamma tau 1 plus delta dot b inverse, okay, where alpha beta gamma delta are integers, okay. After all, you see, if you take z going to z plus 1, it is conjugate by b of an element here, but how does an element here look like? It is translation by an integer multiple of 1 and tau 1, so it will look like this, okay. Similarly z going to z plus tau 2 is going to look like conjugate by b of an element here, which I have taken it in this form. So that is why you get these four integers, and you can guess that they are going to give you the element of PSL to Z. So that is a calculation that one has to do, okay. So let me write it down. So what happens is, if you write it down, this is what you get. So you see, suppose I write it in matrix form, this is 1 1 0 1 b is equal to b 1 0 1 alpha tau 1 beta. I mean, this is just this written in matrix form. I've just pushed I've pushed this b inverse to the b on the right. I have multiplied both sides of the equation on the right by b, okay, and if I write it in matrix form, this is what I get, okay. Similarly, if I do it to the second equation, what I'll get is 1 tau 2 0 1 b is equal to b, well, is equal to b times the other one, which is 1 0 1 gamma tau 1 plus delta. I get this, okay. If you write out, if you make the comparisons and write out, you will see that this is true, these two are true. So this is true if and only if you will see that b equal to 0, and you get alpha tau 1 plus beta is 1 by a squared, where you know this a was this a that we chose for the matrix representative of b in PSL to C, okay. And here you will get these two are equal. I mean, this is equivalent to well, again of course b is 0, and you will get tau 2 by a squared is equal to gamma tau 1 plus delta, okay. This is what you get. Now you can see immediately that you know, if I eliminate a squared, what I am going to get is I am going to get gamma tau 1 plus delta by alpha tau 1 plus beta is equal to tau 2. Okay, so what you've gotten is an element of PSL2Z which is moving tau 1 to tau 2. Okay, now there's a point here, there's a check that has to be done to say that gamma beta gamma minus alpha delta is actually equal to 1. Okay, one has to for example even verify that this is really a Mobius transformation, so one has to really verify that gamma beta minus alpha delta is equal to 1. Okay, it's, for example, it's not equal to 0. So how does one do that? So the claim is gamma beta minus delta alpha is actually equal to 1. Okay, so for this it's enough to prove that gamma beta minus delta alpha is non-zero. See, gamma beta minus delta alpha, if it is not 0, okay, it's an integer, okay, and it has to be invertible because it is a determinant of an integer matrix. Okay, so it has to be an invertible integer. So if you prove gamma beta minus delta alpha is not 0, then you will get gamma beta minus delta alpha equal to plus or minus 1. Okay, then I will have to eliminate the case that it is minus 1, and eliminating the case that it is minus 1 is precisely where I am going to use that tau 1 and tau 2 have real part, have imaginary part greater than 0. Okay, which is a very direct calculation. So let me explain, let me write out that calculation. Okay, so suppose it's 0. Okay, I mean I am trying to give a very elementary argument. Suppose gamma beta minus delta alpha is 0. Okay, then what you do is you use these two equations, use these two equations and try to use the fact that so you know I multiply this equation by delta so that I get a delta alpha, alright, then I multiply this equation by a beta so that I get a beta gamma, and then if I subtract, alright, then this delta alpha tau 1 minus beta gamma tau 1 is going to go away, and if I do that, what I am left out with is 0 equal to beta tau 2 minus delta by a square. This is what I will get. Okay, multiply this equation by delta, multiply this equation by beta, okay, and then subtract, you will get this, right, and you have to use gamma beta minus delta alpha is 0. Okay, you will get this. So but this will tell you that you know beta tau 2 is delta, which is impossible because you see beta is an integer, delta is an integer, tau 2 is a complex number. This will tell you that tau 2 is equal to, for example, if beta is not 0, it will tell you that tau 2 is a rational number, a real number for that matter, which it is not because tau 2 is imaginary, alright. So this will imply the only way is beta equal to delta equal to 0, there is no other way, alright. But you see, if beta is equal to delta is 0, see for example, you know if beta is 0 then alpha is not, if beta is 0 alpha tau 1 is 1 by a square, that is not 0, so alpha is not 0, alright, and what you will get is you will get if I put it here I will get gamma, so I will get alpha is not 0 and tau 1 is equal to 1 by alpha a squared, alright, and if I put it back into this, alright, and use the fact that delta is also 0, I will end up with getting gamma by alpha is equal to tau 2. Okay, so I just cross, delta is 0, I cross multiply this a squared, and a squared tau 1 I write it as 1 by alpha, okay, then I will get gamma by alpha equal to tau 2, which is again nonsense because you see now tau 2 becomes a rational number, gamma and alpha are integers, okay, so that is not possible, absurd. So it is a very elementary argument to show that alpha gamma beta minus delta alpha is non-zero. Okay, so gamma beta minus delta alpha is not equal to 0. Okay, okay, so now we need to see why gamma beta minus delta alpha is actually equal to 1, alright. So for that what one needs to do is to to look again at this diagram here, one has to look at this diagram here and look at it carefully. The first thing that we should remember is that both deck transformation groups, you see, they are they can be identified as Z modules, okay, with complex numbers, okay. So what you can do, so one can write down the following, so let me write down that diagram again. So I have the deck, so I have deck P1, right, here, then I have this isomorphism which is conjugation by B. This is just the map A going to B A B inverse, okay, and this is an isomorphism of the deck transformation group of the covering given by P1 with the deck transformation group of the covering given by P2, okay. And well, you see, this deck transformation group can be identified you see with this is an isomorphism with Z dot so let me follow what I have written down, Z dot 1 cross Z dot tau 1, okay. So what I am doing here is an element here is translation by an integer multiple of 1 and an integer multiple of tau 1, okay. So so it is given by a pair of integers, and I am just identifying that with these two integers here, okay. So there is an isomorphism like this that makes this so this isomorphism actually shows that this is a Z module, okay. This is an isomorphism of Z modules. So similarly I have an isomorphism here. This isomorphism will be in Z dot, it will go to Z dot 1 cross Z dot tau 2 Of course this is because of this, you see deck P1 has generators Z going to Z plus 1 and Z going to Z plus tau 1, and deck P2 has generators Z going to Z plus 1 and Z going to Z plus tau 2. It is only big, and you see these are generators as Z modules, okay. So you have this identification, and now if you look at one would like to look at this map which is given by the commutativity of this diagram, okay. So well, notice that this map is conjugation by B, it has an inverse, the inverse map is just conjugation by B inverse, okay, obviously, and this conjugation by B induces, let me call this as let me call this map, see mind you this map is also going to be an isomorphism, it will be an isomorphism of Z modules, okay. So this is also an isomorphism, and I will get, so this let me call this as gamma prime, okay, and then I will have a map like this. So the conjugation by B inverse is going to induce a map like this, namely this map is this followed by this followed by this, okay, that is this map, and this map is this followed by this followed by this, okay. So I have this gamma and I have gamma prime, okay, and it is obvious that gamma and gamma prime are Z module homomorphisms and they are inverses of each other, okay. Gamma prime are Z module homomorphisms, and of course gamma prime is gamma inverse, okay, by the very way it is defined, alright. Now the important thing is what is the matrix for gamma. See, gamma is a map from 2 copies of Z to 2 copies of Z, so it is given by a 2 by 2 matrix with integers in Z, okay, and what is that map, and that map, see the claim is this gamma, so let us calculate. So take the element 1 here, see this I need to know where gamma of 1 goes to, alright. So take the element 1 here, this element 1 is identified with the transformation Z going to Z plus 1, okay, and that transformation will go to B inverse dot z going to z plus 1 dot b, okay, and then I am going to identify it with this, alright. So but what is go back to this equation here, b inverse dot z going to z plus 1 dot b is actually z going to z plus alpha tau 1 plus beta, okay. So when I come here I will get the map z going to z plus alpha tau 1 plus beta, and if I bring it down here I will get the elements alpha times 1 plus beta times tau 1, so I will basically get alpha comma beta, okay. So gamma of 1, okay, gamma of 1, if you want, what I mean by that is gamma of 1 comma 0, okay, you take 1 here and take 0 there, alright. This is alpha comma beta, okay, and what is gamma of 0 comma tau 2, what is gamma of 0 comma tau 2, see take tau 2, here it will go to the deck transformation which is translation by tau 2, so it will go to z going to z plus tau 2, alright, and here it will go to its conjugate by b inverse, so namely I will get b. So now go back to this diagram and see b inverse z going to z plus tau 2 b is actually z going to z plus gamma tau 1 plus delta, okay. So the image of tau 2 here will be the translation by gamma tau 1 plus delta, and you see if I take its image here I am going to end up with delta, so it's gamma, so it's delta comma gamma, it's delta comma gamma, okay, if I write it in this order, gamma plus delta tau 1, okay, that is what it is, alright. And you see, so you see what this tells you that matrix of gamma is alpha beta delta gamma, okay, and I think I am not writing it correctly, so it is alpha times wait a minute, alpha is a quotient of tau 1, okay, so beta alpha, I should write it here also correctly, it is beta times 1 plus alpha times tau, so it is beta alpha, okay, this is the matrix of tau. And you see for gamma prime also similarly you will get an matrix with integer entries, alright, and what will happen is, you see the whole point is gamma and gamma prime are isomorphisms, they are z moduli isomorphisms, okay. So the fact is so matrix, so let me write this here, beta alpha delta gamma, alright, times let me write matrix of gamma prime, okay, if I compose I should get the identity matrix, okay, and this is, I get this because this is the inverse of gamma prime, gamma is the inverse of gamma prime, that is right, okay, gamma prime inverse is gamma inverse is gamma prime, alright. So I get this, alright, and notice that the matrix of gamma prime will also have integer entries, I mean you have to write it the same way as you wrote gamma, but in any case what will happen is this, see this is the equation that helps me, because now if I take determinant and notice that all my calculations are happening in z, okay, they are happening in z, the integers. So if I take determinant I will get, what I will get is I will get beta gamma minus delta alpha, okay, times determinant of matrix of gamma prime is equal to 1, okay. Now you see I get a product of two integers equal to 1, okay, so the possibility is that either both are plus 1 or both are minus 1, so this will tell you that beta gamma minus delta alpha is equal to plus or minus 1, okay. Now of course one can rule out the case that beta gamma minus delta alpha is minus 1 because of the condition that tau 1 and tau 2 have imaginary part positive, that is because of the following calculation, so let me write that down, so here I am. So if you calculate imaginary part of tau 2, okay, it is by definition imaginary part of, well, tau 2 is now going to be, where have I written it? There I have written it here. Tau 2 is gamma tau 1 plus delta by alpha tau 1 plus beta. So gamma tau 1 plus delta by alpha tau 1 plus beta, this is what it is, and you write the imaginary part of this as this minus its conjugate divided by 2i, okay, you just write it out, and if you simplify it, what you will end up with is you will get delta alpha minus beta gamma times minus of imaginary part of tau 1 divided by modulus of alpha tau 1 plus beta the whole square. This is what you will get, okay. If you make a very simple calculation, you will get this, and you will see that, you see, imaginary part of tau 2 is positive, imaginary part of tau 1 is positive, okay, and this quantity is also positive, therefore you see this quantity has to be negative, okay. So this will tell you imaginary part of tau 1, imaginary part of tau 2 positive will tell you that delta alpha minus beta gamma has to be minus 1, so that will tell you that, well, as we wanted, gamma beta minus delta alpha is equal to plus 1, is equal to 1. So this confirms that you know this matrix, so this means that your matrix gamma is actually an element of PSL2. So gamma is an element of PSL2, okay, it is an element of SL2, and you can take the image defined, take its image in the quotient group PSL2, okay. Consider well, let us consider this, namely the following thing: gamma delta alpha beta, this is an element of PSL2Z, okay, this is also an element of PSL2Z again, and you see this takes tau 1 to tau 2, okay, that is what I want. So well, if I had chosen these constants correctly, I would have got I would have directly got alpha beta gamma delta, but anyway it does not matter. So the point is I have got an element of PSL2 which takes tau 1 to tau 2, alright. So the upshot of the story is, if the torus complex torus defined by tau 1 in the upper half plane is isomorphic to the complex torus defined by tau 2 in the upper half plane, then there is an element of PSL2Z which takes tau 1 to tau 2. Now the point is that this whole argument can be reversed. Conversely, if I am given a PSL2 element which takes tau 1 to tau 2, okay, then one can work out, okay, and one can so in that case, you know, alpha beta gamma delta are given integers such that, you know, gamma beta minus alpha delta is equal to 1, okay, I am given this. So in some sense, so I am given gamma, okay, and from gamma I have to cook up an isomorphism, between these two tori, okay, and how do I do this? Well, because I am given gamma, what I can do is first I can first cook up this B, okay, I can cook up this B which is given by these coefficients, okay, and how do I get these coefficients? Well, you see, I set, if you go back here, I set small b equal to 0, alright, and then I set A to be a square root of 1 by alpha tau 1 plus beta, okay, so I set A like that, and then I consider this transformation A 0 0, and instead of D I put 1 by A, that will give me a Mobius transformation B, okay, and that Mobius transformation you can check will give me that will give me an isomorphism from C to C, alright. Now that isomorphism, because of that isomorphism will actually go down, The reason why it will go down is because the lattice defined by 1 and tau 1, namely the z submodule of C defined by 1 and tau 1 will be mapped to the z submodule of C defined by 1 and tau 2. That is because of the way that is because you are given that element of PSL2 which does this, okay. Therefore this you will get this B, okay, and it will go down to a map like this, okay. You can cook up the B, okay, given alpha beta gamma delta and a PSL2 matrix which takes tau 1 to tau 2, namely for which this holds. I can write down B explicitly. All I have to do is I have to set small b equal to 0, I have to take, instead of D of course I have to put 1 by A, alright, and for A I have to take just square root of 1 by alpha tau 1 plus beta, that's all I have to do, okay, and then I will get this B, okay, and you can check that this B takes any integer linear combination of tau 1 and 1 into an integer linear combination of tau 2 and 1, okay. That's because of the way that's because of the unimodular transformation alpha beta gamma delta that's already given to us, okay. So you will see that it will carry the grid defined by 1 and tau 1 to the grid defined by 1 and tau 2, and therefore it will induce a map like this, okay, and the B inverse will induce a map in the other direction, so this map will be automatically bijective. The only question is why is it a holomorphic isomorphism? It is very simple, because you see what will happen is, well, if I am given B, then B for this is of course holomorphic, it's a Mobius transformation, then this is also holomorphic, therefore this becomes holomorphic, okay. Now this map is, because it is a covering, this map is locally this followed by this, because you see this map P1 is a local homeomorphism, it's a local biholomorphism, so locally this map can be written as inverse of this followed by this by taking an admissible neighborhood at any point, okay. So this map becomes a composition of two holomorphic maps, therefore this becomes holomorphic. In the similar way its inverse also becomes holomorphic, therefore these two tori become isomorphic, biholomorphic, okay. So everything can be, the whole argument can be reversed, okay, the whole argument can be reversed. So the upshot of the story is the following result. So let me write that down. So let me write this just for the sake of completeness. Conversely, given alpha beta gamma delta integers such that gamma tau 1 plus delta by alpha tau 1 plus beta is equal to tau 2, and well gamma beta minus delta alpha is equal to 1, okay. Define B by A001 by A, where A is just given by this formula 1 by root of alpha tau 1 plus beta, okay. Then B induces, then B takes z dot 1 cross z dot tau 1, it takes this subset of complex numbers, okay. So this is set of all complex numbers which are integral multiples of 1 and tau 1, so it is of the form n plus m tau 1. So this will go into z cross 1 z dot 1 cross z dot tau 2, okay. So this will imply B induces f from the torus defined by tau 1 to the torus defined by tau 2, okay, and has and B inverse, of course, and B inverse induces F inverse, okay. The only thing that is left is to see that F is holomorphic. That is because F is holomorphic since so let me draw a small diagram and rub this side. So let me draw the diagram and then come back here. So I have C to C, I have B, and this is P1, this is the covering projection for the torus defined by tau 1, and this is P2, the covering projection defined by torus defined by T2, okay, and this is my F, and this diagram commutes, okay, and well, this map is going to be B P2 circle B, that is what this map is. So it is this followed by this, okay, and well, and of course this diagram also commutes. So what I am going to say is that F is holomorphic since B circle P, P2 circle B, P2 circle B is holomorphic, okay, this is holomorphic because it is a composition of holomorphic maps, and because P1 is locally biholomorphic, and P1 is locally biholomorphic, okay. Therefore F is an injective holomorphic map, so it is a biholomorphic map, and therefore we have proved that the tori are isomorphic. So you see, therefore the moral of the story is that what I can do is from U to the set of all complex tori, isomorphism classes of tori which are the form T tau comma 1 tau belonging to U mod isomorphism, okay. I have this map tau being sent to T sub tau comma 1 isomorphism class biholomorphic isomorphism class, holomorphic isomorphism class. Then this map goes down to a map to the quotient U mod PSL2Z, okay. So I have the quotient U mod PSL2Z. This is the set of orbits of PSL2Z on the upper half plane, okay, and well 2 points go to the same point here if and only if they are movable by an element of PSL2Z, that is what we have proved. So you get a map like this, now this map is of course by definition surjective, therefore this is also surjective, and it is also injective because for the simple reason that, you know, if you have tau 1 and tau 2 which give rise to isomorphic tori, then tau 1 and tau 2 have to be in the same orbit of PSL2Z. So this also this is injective as well as surjective, so this is a bijection. So you see, this completes the proof of the fact that the set of isomorphism classes, holomorphic isomorphism classes of complex tori is bijective to this set, namely the set of orbits of PSL2Z in U, okay. So this is the first part of the story. Now what we will do in the next lecture is to show that this is a Riemann surface, okay. You have to show that this is a Riemann surface and that this map, this bijective map, okay, one wants to show that this is a Riemann surface, and one also wants to show that this is actually and the Riemann surface that it is actually the complex numbers, okay. That is what one wants to show, right. So that is the next part of the story, right. So we will continue the next lecture, right.